Hello students, welcome to Inside Physics. In this video, we are going to discuss about diffraction due to double slit. Fraunhofer diffraction. In the previous video, we discussed about single slit and we derived the formula for resultant amplitude and resultant intensity. Here, we will do double slit experiment and what is the interference pattern and what are the variations of intensity considering single slit and also double slit, two slits here. As per the Fraunhofer diffraction, we use two lenses. Here in this diagram only one lens is picturized. Another lens will be here, making the incident wavefront as a plane wavefront that I also explained in the single slit experiment. So there will be a source here, there is a lens and the plane wavefront is incident on the two slits. So here the diffraction pattern from the slits is considered in two ways. So here according to Huygens wave principle, the primary wavefront, plane wavefront incident on the two slits, each point in the slit, if you look at the diagram, this is slit 1, this is slit 2. So both have the same width A and this is also slit 2 is having width A. The B, width B is the width of this opaque medium. So XY is an opaque medium where A, B, C, D are two slits arranged. A slit is a passage of light where it is very narrow passage. We know the diffraction pattern is nothing but bending of light at the edges of the obstacle. If any obstacle is encountered by light, it bends at the edges. That pattern is called diffraction pattern. The property of light bending at the edges of an encountered obstacle. Here the slit is considered as an obstacle. Even though some rays are passed without any diffraction, the edges is causing some bending of the light waves. The light waves are passing through the slit. Here the waves are considered as wave fronts. According to Huygens theory, we can explain on the basis of wavefront theory this diffraction pattern in a better way. So whenever a plane wavefront is incident, this edge makes the wavefront bend like this. So by the passage, we mean that the width of the passage or slit is equivalent to one wavelength of light, or it must be less than one wavelength of light, so that the diffraction pattern appears. So if the passage of the slit is, width of the slit is high, we cannot see any diffraction pattern. So here what happens, we see when the incident light ray is passing without any deviation, these are the rays without any diffraction, so they will be parallel to the principal axis of this lens. So this is a converging lens, convex lens, and all parallel rays, paraxial rays which are parallel to the principal axis will converge at the point P, which is in the focal plane of this lens. So this screen MN is the screen through which we observe the diffraction pattern by a microscope, and this point P is exactly at the focus of this lens. So we can clearly able to see the diffraction pattern. So diffraction here is understood in the form of two ways. See, diffraction pattern through a single slit. In this way, each point in the slit will emanate the secondary wavelets. The plane wavefront, primary wavefront will hit the slit, then each point on the secondary wavelets will be emanating from the slit. So here the first pattern is the diffraction due to single slit, and the intensity variation also we can see in that diffraction pattern. The second one, we can understand this by overlapping of the interfering diffracted waves from the corresponding points of two slits. If there is a wave which is diffracted from this point, from this slit 1, so this is going in this way, and there is a corresponding point in the second slit, so that the wave will also diffract, and these two waves will interfere to form the interference pattern due to diffraction. So in these two ways we can understand the diffraction pattern. Now we will see what are the terms in this diagram. If this is the value of theta, which is angle of diffraction, this is also called theta, which is angle of diffraction. So the angle between the undeviated ray to the diffracted ray is called angle of diffraction. So if you consider these two rays and draw a vectorial diagram, so we can see the resultant amplitude. This is having an amplitude and this is also having an amplitude. The term, the formula, we can write it as a theta is equal to a naught into sine alpha by alpha. This is what we have written in the derivation while we are doing the single slit experiment. So here a naught is the amplitude of the original wavefront coming from the source. A source will be here, which is not shown in the diagram. So from here there is a lens here to make it as a plane wavefront. These two things are not shown in the diagram. So here the plane wavefront incident on the two slits a theta, this is nothing but amplitude when the diffracting angle is theta, resultant amplitude when the diffracting angle is theta. We already know alpha is equal to pi d sine theta by lambda. This is derived from the previous derivations, where d is the width of the slit. Here, what is the width of the slit? Pi a sine theta by lambda. Here a is the width of the slit. So by considering this and considering these undeviated ray and diffracted ray as a vectorial diagram, we can see if this is considered as delta, the phase difference between the diffracted ray and parallel ray. So this resultant, can consider this as a resultant or resultant amplitude. If these two waves are having a phase difference and they are overlapping to form the interference pattern, the resultant of the amplitude can be taken from the parallelogram law. Here I can write this ON or the resultant R as this, in this form. So what is this? Written as R square is equal to OM square plus MN square plus 2 OM MN cos delta. So here where delta is the phase difference. Okay. Here see, if this is the undeviated ray, this is the diffracted ray. What is this amplitude of this wave? The original amplitude into the sine term. So this is also having the same term regarding the amplitude. So where alpha, already we have written alpha is pi a sine theta by lambda, where a is the slit width. So this term represents dependent on the wavelength of the light and the diffracting angle and the slit width. So what is the resultant amplitude? We can write it as R square is equal to a naught square, or we can write it as a naught sine alpha by alpha whole square plus a naught sine alpha by alpha whole square plus 2 into a naught sine alpha into a naught sine alpha by alpha into cos delta. Okay, so this is the vectorial picture, and I am erasing it to derive the resultant amplitude in case of a double slit. So here, if you observe this, this can be written as 2 a naught sin alpha by alpha square plus 2 into a naught sin alpha by alpha whole square cos delta. So if you take the common factor from these two, a naught sin alpha by alpha whole square, then this can be written as 1 plus this term and this term are taken the common factor, and this will become cos delta. Okay, we can write in this way. So this term cos delta, we know from trigonometry what is cos delta. That means what is cos 2 theta has a formula here, 2 cos square theta by 2 minus 1, 2 cos square theta by 2 minus 1. So in this form we can write the cos delta in this form. So what happens? So make a note of this formula. This can be written as a naught sin alpha by alpha whole square. So here 1 plus 2 cos square delta by 2 minus 1. Okay. So here minus 1 plus 1 will be cancelled, and this term will become a naught square sin square alpha by alpha square cos square delta by 2. So in this way we can write this term from here. 2 into 2 will become 4, and this is squared with each term, a naught square sin square alpha by alpha square cos square delta by 2. So this I will write it as, see, r square. This is the resultant amplitude. So I will write this resultant amplitude r square is equal to 4a naught square sin square alpha by alpha into, I will take here delta by 2 is equal to beta as for the calculation purpose, easy calculation. So this can be written as cos square beta. Okay, if you observe this one, we already know the intensity pattern, the intensity of light, while the interference and diffraction pattern here, both interference and diffraction patterns have variation of intensities, because diffraction has also variation of intensities, and the interference, where is the interference pattern here? The corresponding wavelets, secondary wavelets from each slit 1 and slit 2, they will be overlapping and they will form an interference pattern which also has variation of intensity. We already know the intensity of light is directly proportional to amplitude square of the light. So by this relation, this can be rewritten as, this is considered as resultant amplitude square means resultant intensity I can write it as I, the resultant intensity, and here if you observe I can write 4 I naught. So only these two terms are exchanged because the intensity is directly proportional to amplitude. So what about these terms? Sin square alpha square, here square, okay, sin square alpha by alpha square into cos square beta. Now we analyze this one. So for minima and maxima, low intensity or zero intensity, high intensity. So we must get the conditions based on this relation. What is the condition for minima? What is the condition for maxima? Here you can observe these two terms. This is this one and this one. They both have some significance considering the interference and diffraction pattern. This term will be indicating the variation of intensities of diffraction pattern due to single slit. So this term will indicate the variation of intensity pattern in the overlapping condition. That means in the interference pattern it indicates the variation of intensities. So in both cases we have a combined relation for double slit. So these two have their own physical significances. So how we should get the minima and maxima conditions here, and we will do with some values of theta. So if you observe this one, for condition of minima, what must be sine alpha value? Minima means there must be zero intensity. So if sine alpha is equal to 0, this whole term will become 0. Then this will be suitable for the minimum intensity condition. So here what are the values that we can give to alpha? For sine alpha must be 0 means we can give the plus or minus m pi, where m is equal to 1, 2, 3 and so on. So these values we can give to the alpha so that sine alpha will become 0. So in this sense the condition for minima is arrived. So what is alpha? We know that alpha is equal to pi a sine theta by lambda is equal to plus or minus m pi. So if on both sides, if you remove pi, what happens? Sine theta is equal to plus or minus m lambda by a. So this value of sine theta, so the diffracting angle can also be calculated if you know the order of the fringe and wavelength slit width. So where m is the order of the fringe. So in this double slit experiment we can see the central maximum. So zero order central maximum spot is P. So why centrally maximum intensity is there? All the undeviated rays are focusing at P due to the convergence. So here the central maximum will be bright and the alternate dark and bright rings are formed besides this central bright spot. Okay. So this is the condition for minima, and here the condition for maxima considering this term, sine term. What is the condition for maxima? That means if sine alpha is equal to 1, then this term will be at its maximum value, because sine alpha, sine theta, function of sine will always variate between -1 and +1. That is the range of sine function. So here if sine alpha is equal to 1, what must be the alpha values? This is equal to odd integral multiples of pi by 2, where m is equal to 1 comma 2 comma 3 and so on, but not 0. So here the alpha value is given in this way, and what is alpha? We already know, pi a sine theta by lambda is equal to plus or minus 2m plus 1 into pi by 2. So the angular positions for maxima can be taken as, so if you consider in the bracket what is the values are going to be, they are like 3 pi by 2 comma plus or minus 5 pi by 2 and so on like that. So these angular positions will be providing the maximum intensity while forming the interference pattern. So here the minima condition is also should be considered for other term. Which is the other term here? Cos square beta. If for minima this must be 0, right? So if this must be 0, what are the beta values are going to be? Cos 0. What are the beta values are going to be? So this beta must be equal to plus or minus odd integral multiples of pi by 2. So where m is equal to 1, 0, 1, 2, 3 like that. Okay. So in this way the values can be taken for minima and maxima. So what are the other values? So for this beta is, we already know, is delta by 2 plus or minus 2m plus 1 into pi by 2. So this delta, what we have taken, delta is equal to phase difference 2 pi a sine theta by lambda. This is all we are getting these values from the previous single slit derivation, and this is the way to get the conditions for maxima and minima. So if you observe the conditions here, it is all dependent on the diffracting angle, right? So for other term, cos term, what is the maxima condition? If cos square beta is equal to 1, then the condition for maxima is satisfied. So what should be the values for beta? These values must be plus or minus m pi. If m is equal to 0, if then theta is equal to 0, what happens? And this value becomes 1. So where m is equal to 0, 1, 2, 3 and so on. So we all know delta by 2, beta is equal to delta by 2, and if you place this value in here, we can get the phase difference if you know the diffracting angle. So this is the conditions for maxima and minima, and here we picturize these patterns in the form of a graph to understand better. So we will close this session in next 5 minutes after drawing these pictures, taking x-axis, y-axis like a coordinate system, and the alpha values here, if you consider them as 0, pi, 2 pi. Okay, what are the minima conditions that you observe in the diffraction pattern? The centrally, if the alpha, that means the diffracting angle is 0, the intensity is the brightest, so bright spot will be appearing. So here also in the negative side we can consider as minus pi, minus 2 pi, minus 3 pi like this, and here also we can consider. So the central bright spot will be having very high intensity. Okay. So another bright spot here, minus pi to pi. What happens? There will be a second order bright ring, and there will be a further less density second order, and there will be much more lesser density third order. This centrally bright spot can be called as zero order or first order bright spot. Okay. central maximum. So if you observe these values, these are said to be minima. Maxima, minima, maxima, minima, maxima and minima. These are the maxima terms. So where you will get the one positive value for this sine alpha. So this is the pattern for the single slit diffraction pattern. If you observe this term, that means when the interference pattern is done because of the two slits, this picture, this diagram can be taken as so here the beta values are taken on the y-axis, and here to both on both sides to consider what are the beta values. We must consider same as the due to what you consider for alpha 2 pi, 3 pi and pi values here minus because of the negative side. Here if you observe the patterns, it will be the intensity of the patterns will be same for all the diffracting angles. So if you observe here, this is the intensity pattern. So minus 3 pi, here you can take minus 3 pi. So this is the overlapping. This is what the interference and diffraction will have a variance. The difference, the particular difference here is the variation of intensity is same. The intensity is same in case of a overlapping condition, interference pattern, and you can see the intensity in all the cases is same. But in diffraction, what we have seen earlier, it is the intensity is decreasing from zero order to second, third orders of the bright spot. So the intensity is decreasing while we move from the central bright spot in the diffraction pattern. So this is all the theory about the diffraction and the due to double slit, due to two slits. So in the next session we will come up with another interesting topic in the wave optics. Thank you.